Okay, now we're going to wrap this all up. We're going to take everything we just learned, um, everything you learned about the celestial horizon, about your altitudes, about zenith distances, everything you learned about declination, about GHAs and LHAs, and about assumed latitudes. All of that is going to be put together now so you can actually see what the process of calculating calculating where your position is, or at least finding one line of position using all of that. So I've set us up here. Here's the equator, here's the prime meridian. This is just generally, a big map of the Earth. That's our position, or at least that's our assumed position. We don't know where we are, but our assumed position is right here. And the assumed position is almost always within 30 minutes, so 30 miles of the true position. Technically, it just has to be within a degree. It can be separate from that, but it's smart to keep it within a degree. So we're somewhere around here, but our assumed position is right here. And then here's the sun right here. So I want us now to label everything we know. Well, if that's our assumed position, then that is our assumed latitude. And if this is our assumed position, then that is our assumed longitude. Obviously, these are the two components that go into calculating your assumed position. Now, here's the sun. We know that that is the GHA of the sun. We also know that that is our declination, usually contracted as just dec. And that's how we define the location of the sun. Well, now if we start looking into the relationship between the two, we know that if we're in the east and the sun is in the west, or the sun or whatever the body is, GHA is longitude or assumed longitude plus, or LHA is assumed longitude plus GHA. We know it's always going to the west from our position. So we also know that that right there, being assumed longitude plus GHA, is our LHA. And these are the three important ones: our declination, our assumed longitude, and our LHA. Because what you can see we've done is we've created two vertical lines and a horizontal line. And I'm not going to explain the trigonometry because I couldn't actually derive the equation myself, but I think it's pretty easy to see now that it's not that hard mathematically to calculate this. Given this and this and this, just three sides to a total quadrilateral, you can pretty quickly calculate what this final bit is. If anything, if we shifted the LHA up to here, now we just have a right triangle. All we did is remove the assumed longitude and remove the assumed longitude from the declination, leaving just the difference between the two. And then we would have a right triangle, and now it's very easy to calculate. It also means that we can find both this distance and this angle here from the vertical down to the angle aiming towards the sun here. Basically, from your position looking at the sun, what is the bearing from it? Now, this angle here is called your azimuth. Either written as, azimuth. Technically, in the math, you'll usually get your azimuth angle, and then you have to convert it to your azimuth itself. Azimuth angle being written as ZA. Sometimes I've seen AZ, and then azimuth itself being ZN. just the same as in your great circle sailings, the difference between course angle and course. But that's your azimuth. Now I want you to ask yourself, what is this? This is the distance in arc, so in degrees, from your assumed position to the sun. Well, if we go back to the horizon system from before, this one, we have that right here. Here's our position on the celestial sphere, and here's the body. So we already labeled and defined this distance here. This is our zenith distance, ZD. So in other words, if you have your assumed longitude and your declination of the sun and your LHA, you can calculate your azimuth angle, which can then be used to calculate your azimuth, and you can calculate ZD, being your distance away from the sun. Why is this important? Well, ZD is actually not that important other than the fact that if we go back, ZD is just 90 minus the altitude of the sun above the celestial horizon. So using your ZD, you can just take the complement of that, whatever remaining angle adds with it to 90, and that is the height of the sun above the horizon. So if we now imagine, remember, here's our position, so our zenith is also right here. Let's say the celestial horizon is somewhere over here. It's too big for us to represent cleanly. Let's just say it's this big circle out here on the side. If this is ZD here, then this is HO. HO, HA, again, I'll get into the difference between the two later. HO is technically the most accurate form, the observed height, being the exact true height from the celestial horizon up to the body. So through all of this quadrilateral, these three sides can be used to calculate this, which you can then use to just do 90 minus and find this, completing the arc from your zenith to the horizon, getting you HO. Technically not HO, but I'll talk about that later. The reason all of this matters is, if you remember, none of this involved a sextant. You know your assumed longitude and your assumed latitude based off of your DR position, so off of the chart you've been using this whole time. You know your GHA of the sun and the declination of the sun based off of using the nautical almanac, something we'll talk about later. And your LHA is calculated from those two things we just talked about, from your GHA and your longitude. And with all of that, you were able to calculate your zenith distance and your azimuth and use your zenith distance to find your HO, all without using a sextant. But it's all based off of your assumed position, meaning none of this is actually perfectly accurate. However, if you use a sextant and you actually measure the height of the sun above the horizon, if you measure this angle here, you can now corroborate how accurate all of this is. Because when you measure the sun above the horizon, the first thing you're going to find is HS, which is the sun, the visible horizon up to the sun. But then you can apply your the main body, no, not the main body, correction. Dip. You apply, I forget which correction is which. I think it might be your main body correction. No, it's your dip correction. Your dip correction, we'll talk about later. You apply your dip correction to get from HS to HA, then you apply your main body correction to get from HA to HO, and now that you have HO, you have the true height, the true distance in angle, the true arc from the horizon to the sun. So you can come over here and you could say, this is the HO that I calculated off of all of these calculations. So I'm actually going to write that as HC because it's the height that I calculated. But this right here is my HO. My HC was, for instance, like 65 degrees. That was what I did to calculate all this math. But my HO was only 60 degrees. Well, what you would do is you have to shift everything over because the sun didn't move. The sun is still where the sun is. So the HO isn't this. The HO is the same thing offset, so it starts at the sun. Meaning that distance is HO. Meaning your actual celestial horizon was a little bit closer than you would have thought based off of your assumed position. And what that forces you to do, because this is still has to be 90 degrees, is it shifts your assumed position back the same amount. So if this was a 5-degree difference between HC and HO, it meant that HO or HC had to be backed away by 5 degrees, causing ZD to be backed away by 5 degrees, causing your assumed position to be backed away up to here. Meaning comparing the difference between the height of the sun that you measured off of the sextant and the height of the sun that you calculated will automatically show you the difference in distance along this bearing that your true position is compared to the assumed position. Whatever value you get as the difference between these two numbers, that's how far away you are from your assumed position. And luckily, it's not just in any direction you're this far away, it's exactly along this line. Either HC was too big and you had to shift everything backwards, thus pushing you away, or HC was too small and you had to shift everything forwards, pushing you this way. Always along this angle, which is your azimuth, which is your ZN, which you've already calculated. Meaning, you can just say, if the difference between the two is 5 degrees pushing me that way, my true position must be 5 degrees this way from my assumed position. Now, the one caveat to that is technically all of this math works whether or not your assumed position was here or here or here or here. You chose this arbitrarily, so you can't say with total perfect confidence that your lateral direction was accurate. You know that if it was here, it would still push you back here. If your assumed position was here, it would still push you here. If your assumed position was here, it would still push you here. If your assumed position was over here, it would still push you here because all of this would still work. Like if your assumed position was way over here, then your HO would have been way smaller, causing your HC, or your HO would have been bigger, causing your HC to push you back this way again. Everything works to push you back in this direction until ultimately you can recognize that what you have is a line of position, an LOP, that is perpendicular to the azimuth. It's exactly 90 degrees offset from the azimuth, and it's the distance you calculated here away from it. So if HO is smaller than HC, we have to push HC back because we've moved the horizon backwards because HO was smaller. In other words, this distance, we know the sun has to be at the end of this HO, so we have to move this distance to over here, meaning the horizon has to shift back, meaning the ZD has to shift back, and you get to over here with a line of position of being anything perpendicular to the azimuth passing through that point. So in other words, the whole point of taking a measurement of the sun is to compare the height of the sun to the height that you calculated the sun should be at your assumed position. And when you find the difference between the two, the difference that you chose to add into the problem, because you arbitrarily selected the assumed position, you then automatically find how far away you are from the assumed position in a certain direction. And then you create a line of position in that direction, like so, giving you a true location somewhere along this line. If you did this 3 times, then you would have an exact fix. I know this is a lot, and I don't expect that to have made sense right now, because I'm kind of rambling incoherently and pulling together like 7 different concepts that you literally just learned. But it's extremely important that you can actually visualize what's going on here, so you don't just go through the phases, the steps of all of this without really thinking about what you're doing. All of this serves a purpose. The first thing you do is you measure the height of the sun, and then you just keep that off to the side. Then, having marked the exact time that you did that, you pick your assumed latitude and your assumed longitude. You calculate what the GHA and the declination of the sun were at that exact time. You use these two known values to find your LHA. And now that you've built the quadrilateral here, you use it to calculate your zenith distance and your azimuth. And then the equation actually automatically switches from your zenith distance to your HC. You don't have to do the work there. It will pump out at the end your HC, which is just 90 minus the zenith distance, as well as your azimuth angle over here. And then once you've got HC, you compare it to HO, find the difference between the two. You convert that difference from degrees. Usually it's not going to be in degrees, it's going to be in minutes because there's such a small difference, but minutes of arc to nautical miles. And then having found that distance in nautical miles, you apply that distance to your assumed position, either towards it if HO was bigger, or away from it if HO was smaller, in the direction of the azimuth, either along the azimuth or away from the azimuth. And then once you've gotten that distance, you create a perpendicular line and you have a line of position. This isn't magic, this is math. And if you want to, you can understand exactly what's going on here. You don't need to just trust the process. I want you to know what the process is doing.